Okay, the last thing we are going to do is this example number 23 for Friday's class. It's a projectile launcher, as we used in class. It's made with a spring having spring constant K to be 5 pounds per inch. The launcher shoots a 2.5 ounce ball at an angle of 35 degrees. The ball reaches a maximum height of 8.5 feet above the launcher's exit. And that's kind of there are 3 points shown, 1, 2, and 3, and the 3 is where that maximum height is. And we'll determine the speed of the ball when it exits the launcher, and so it's at point 2 in the middle. And the amount of spring was initially compressed, so that's for related to point 1. Okay, because point 2 is relaxed spring, so it was compressed that way, and we are also looking for that too. Okay. Okay, so this is kind of the setup. Now you can see that the problems are getting more involved, and you need to go back, and that's why I've been saying like the chapters are really built up on each other. So you need to go back and kind of use some knowledge that you learned before, and you will see what I mean by that when we get to the solution for part A. So first thing, we are trying to find the ball's launch velocity. That is on the point 2, right? So we are looking for kind of V2, and the ball amount of spring compressed. So that is happening at point 1. So I don't know 2 things, and those are the velocity of the ball and the amount of the spring compressed, and those are the points like 1 and 2. So hopefully, like you can see that now, there are several ways you can solve this problem, but one of them is using energy conservation. And there are 3 points now. It's not just from initial to final. There are 3 different points. So you gotta make a plan, okay? First off, let's start with the assumption. We are going to neglect air resistance, the friction in the gun, in the air, or there's no air resistance either. Later on, I also talk about this, but there's no temperature change, no heat transfer, and spring is relaxed at point 2 when the ball leaves the muzzle, so there's no more stretch or compressed at point 2, and we will make use of those informations, okay? In the figure, if you analyze in terms of energy transfer, if you look at point 1, we first of all compress the spring, right? And we put the ball at point 1. So in that case, the object is not moving, so kinetic energy is 0. Gravitational potential energy, since we did something different here, and I want to highlight that. We did say point 2 is y equal to 0, and that's fine, but that makes the potential energy, gravitational potential energy, negative for 1, because point 2, which is 0, is higher elevation than point 1. Okay, you're looking at the elevation, you're looking for upward, okay, not sideways, just upward. So that's going to be below the 0 line, so it's y takes a negative value, and we are going to discuss that later. And in terms of elastic potential, it's the highest because there's a compress, and the maximum compression is at point 1. At point 2, again, this is the highest high kinetic energy because the spring is now released, and it has that maximum velocity between those 3 points. And gravitational potential energy will be 0 because we chose again y to be 0. And elastic potential energy is also 0 because spring is relaxed. Okay, those are the reasons. At point 3, this is the maximum height. First of all, please kind of don't forget that because it's important. We will use that information later. Lower kinetic energy than point 2, but it's not 0, so it's higher than point 1, lower than point 2 in terms of kinetic energy. It's going to have highest gravitational potential energy because this is the maximum elevation it goes. Again, it's related to this y. And elastic potential is 0 because there's no spring, right? Okay, so plan is again using energy conservation and projectile motion, because what you see from 2 to 3 is simply a projectile motion problem. So we have to use some of those informations, which is from chapter 4. Okay. Estimations. If you want to estimate the launch velocity of the ball, again, in terms of meters per second, it should be quite a few meters per second. I would probably say like 10 meters per second in order of magnitude instead of 1 or 100. And in terms of the spring compression, kind of try to recall the launcher we used. It wasn't really that big, and the launcher itself was about probably less than a foot. So I would say, I don't know, maybe half a foot or something, or a couple inches. That's the compression length. Okay. So let's begin with the conservation of energy. We have 3 points, 1, 2, and 3. So you can really do 1 to 2, 2 to 3, 1 to 3, because energy conservation, there's no condition. You can apply it, okay? But which one do we choose? So the way I choose is I look at the unknowns I have. I have an unknown at point 1 and unknown at point 2 for sure. Okay, maybe there are some hidden unknowns as well, but those are definitely unknowns. If I use 1 to 2, I already have 2 unknowns and 1 energy conservation equation. I won't be able to solve it yet. So I'm not going to do 1 to 2. Instead, let's do 2 to 3. Although it might look like there are some hidden unknowns, we will figure them out. Okay, so we are starting from 2 to 3, kind of the projectile motion. You can also kind of use projectile motion to figure things out, but since we are working on energy conservation, we are gonna use energy conservation for this part. So I'm writing the energy conservation. That's step 1. Okay, just full equation. Again, we split delta U into 2 parts, gravitational and elastic, as you can see in the equation. And the the work done doesn't really include the weight force or spring force, but we will highlight that later. So you write your energy conservation equation and you draw your Firba diagram. Okay, so you want to see how many forces acting on it. The only force is the weight force, because the object is in air, right? And it's a projectile motion. There's no air resistance, there's no wind, there's no air drag. Since this is the only one and you're already keeping gravitational potential energy, the weight term is going to go to 0, because this is simply this, right? WW, and this is already accounted as delta UG. So kind of get rid of that. This term goes away. Heat is also not added or subtracted. We already mentioned, but I usually write it in here too. No heat added or taken away from the system. What about delta I? That is also 0, because there's no temperature. There's no temperature change or pressure change, so these are 0 as well. Okay, P and T, pressure and temperature. That's why the delta I is going to be 0. I might have shown this in the previous problem wrong, because I think I said it's not equal to 0, but I think what I said was there's no change, so they are 0. Okay. Okay, so do we have between 2 and 3? Again, this is the focus. Do we have spring? Just because the problem has a spring, it doesn't necessarily mean there will be elastic potential change, and we don't have spring between points 2 and 3, so that goes away as well, because I'm gonna say no spring between 2 and 3.